All right, so let's go ahead and begin. Hi, everyone, and thank you for attending this International Programs webinar titled Leveraging Data Analytics for the Integration of Distributed Energy Resources. My name is McDonald, and I am a Senior Manager with the International Programs Department at the Edison Electric Institute, and we are really thrilled to host this very timely webinar featuring a presentation by EEI member Jemena. The topic of DERs and their implications for energy grid management is a critical one for the electric power sector as more DERs come online in the years ahead. And in this webinar, Jemena will walk us through their very exciting journey to create an advanced data analytics program which incorporates new approaches to data supply and network modeling to more proactively manage their network, which has a lot of growing DERs coming online. So we will have time for questions at the end of the webinar, so please use the chat feature. It's located on the right-hand side of your screen to submit questions throughout the presentation. And as an important note, this presentation and webinar is being recorded, and a copy of the recording as well as the presentation file will be shared with all of you after the webinar today. So without further ado, it's my pleasure to introduce Jiangxia Zhong, who is a data analytics engineer with Jemena, who is going to take it away.
Thanks, Jessie, for the introduction. I'm glad to have this great opportunity presenting our work, leveraging data analytics for the integration of DER. So let's start. Here's the contents of my presentation today. It includes the background, the integration of DER, which can be divided into building analytic platform, identify the problem in LV network, improving DER hosting capacity, and the conclusion at the end of my presentation. SGSPAA, trading as Jemena, is an Australian $11.5 billion company that owns, manages, and operates some Australia's most significant gas and electricity assets. Jemena is backed by the strong resources of our shareholders, State Grid Corporation of China and Singapore Power. State Grid Corporation of China is the largest utility in the world, and Singapore Power is a leading energy utility company in Asian Pacific and one of the Singapore's largest corporations. JEN, as known as Jemena Electricity Network, is one of the 5 electricity distribution networks in Victoria. We are the sole distributor of electricity for more than 950 square kilometers of Melbourne's northwest suburbs. We provide energy to support more than 350,000 homes and businesses, as well as critical infrastructures, such as Melbourne Airport. So let's talk about the advanced metering infrastructure, AMI, which provides the fundamental data for our data analytics work. A little bit background for AMI. In 2009, the 5 electricity distributor companies in Victoria started to roll out the smart meter in a program mandated by the Victorian government. The program was completed by 2014. So far, Victoria is the only state in Australia mandates the rollout of smart meters. AMI is automated two-way communications between smart meters, electricity distributor, back office system, and the electricity market. Smart meters have now been providing benefits that have never been available with the traditional metering setup, taking up the flexibility of dynamic pricing to match customers' own consumption behavior, connecting and disconnecting remotely, feeding generations from solar PV panel back to the grid, and gaining credits has essentially changed the electricity being consumed. Apart from standard functionality of smart meter, we can also have 30-minute interval data and even 5-minute snapshot of voltage, current, power factor data by updating the AMI network and the data management system. So the question are, how does the smart meter data benefit customers and the utility companies? How to extract the benefits from billions of readings? How can we transfer the benefits into dollar value? Based on the question, let's talk about the opportunities. Here's one of my favorite presentations recently, presented by Masayoshi Zhong, who is the CEO of SoftBank. You see a picture on the left, which is an actual picture of Fifth Avenue in New York, 1900, and we can see all the carriages on the street with only one automobile. 13 years later, same place, we can see mostly engines and with only one carriage. With more mature AI technology today, we can foresee self-driving car taking place in 2035 at Fifth Avenue, New York. We don't see this opportunity every day. It happens, this one thing in 100 years. So now it's definitely golden age for digital transformation. For the electricity power industrial, it has been developed for more than 100 years. Now it is a great time to transfer from traditional power industrial to industrial 4.0 by bringing latest concepts like Internet of Things and analytic skills like implementing AI to improve the industrial performance. Back to smart meter data. Now we know the big data technologies, data analytic tools such as server programming language, advanced algorithms such as machine learning, optimization are all available. We just need to collaborate smart meter data and our data analytics skill with engineering knowledge to build an appropriate model to solve the problem. Here's the analytic journey of Jemena. After AMI meter rollout, IBM Cognos, an Excel-based tool, has been used for basic network data report from 2015. The reports give us the insight of our distribution network, like substation loading report, but there are some limitations in terms of no visibility to see the neighboring customer substation in a geographical view, no supporting big data environment with programming capabilities. From 2016, by using 5-minute snapshot data and the programming language R, network models and visualization tools has been implemented to become products. It is very exciting that our data analytic work, unlocking benefits of smart metering, has been recognized and won 2019 Asian Power Awards, Smart Grid Projects of the Year, Australian. In the future, once the data quality and the analytic platform has been improved, real-time applications like demand response can be realized. So let's move to the second part, integration of DER, which includes 3 steps. First one, build advanced analytic platform. Second one, identify the problem in LV network. Third one, improve DER hosting capacity. So what's DER? DER is the name given to renewable energy units or systems that are commonly located at homes or business to prove them with power. Another name of DR is behind the meter, because electricity is generated or managed behind the electricity meters in the house or business. DR includes PV, energy storage, electric vehicles, and other controlled loads. Why is DR so important? DR play an important role in reducing carbon footprint. Energy Network Australia announced the statistic that the capacity of rooftop PV increased from less than 10 gigawatts in 2015 to almost 80 gigawatts in 2050. The capacity of battery storage rise from less than 1 gigawatt hour in 2015 to around 95 gigawatt hour in 2050. At the same time, customers can reduce their electricity bills by incentives and lower network charge. However, our electricity network hasn't been tested for the dramatic increase in PV penetration to meet the requirement of Australian standard distribution voltage limit between 260 to 253. As an electricity network provider, we definitely need to review our network before it gets worse. Jemena's long-term objectives for DR will be increasing DR hosting capacity with a focus on the LV network. DR service available to our customer when they want and how they want. Developing distribution system operation capabilities. So far, we have been working on the first objective. Our approach for increasing hosting capacity is to increase visibility of the LV network, introduce LV circuit modeling, identify distribution faults, analyze voltage regulation, and develop the optimization strategy. To achieve our approach, let's talk about the step 1, advanced analytic platform. As engineers, we design a simple data architecture to meet our requirements, which includes data source layer, data pre-processing layer, data storage layer, and the analytic layer. The data in the data source layer is provided by our IT department. Our analytic platform was developed using R software running on a virtual server. The data analytic model were designed and developed in-house. The technology used for data analytics were machine learning and optimization-based algorithms. So apart from data architecture and the models design, we spend a lot of time on visualization tool based on our Shiny package. The tool provides visibility of network and flexibility to the users by customized GUI, desktop analysis of customer supply complaints, and data algorithms verification. I will show more visualization cases along the presentation. So let's go to step 2. Identify the problem in LV network, which includes phase identification, impedance measurement, and network fault analysis. So why is phase information so important? Phase information improves the accuracy of customer connection information to avoid the wrong outage notification to customers, especially for life support customers. A wrong planned outage notification not only damaged customer reputation, but also caused penalty from Australian energy regulators. Phase information is also the for three-phase L. Because phase information is not recorded or recorded incorrectly in GIS, and verifying the phase information by site time-consuming due to Australian LV circuits can be run hundreds of meters from a distribution transformer. A desktop solution should be provided. So here, phase identification model is to calculate and verify the customer connection phase. I have built two models for detecting the phase. Model 1, if any three-phase meter in the circuit can be used as a reference, a correlation-based algorithm is employed to compare the voltage pattern between reference and the Model 2, if there are no three-phase in the circuit, machine learning is employed to analysis into three groups. The models are able to identify the phase information for 90% snapshot smart data. The accuracy is verified by phase outage data and also our super user, power quality engineer. They never complain any accuracy issue. Here's the comparison between GIS software and our visualization tool. Our schematic data is extracted from GIS, which gives us a full vision of the network connectivities and selected asset information to provide the efficiency of desktop analysis. The color code of customer in red, green, blue, orange refer to the red, white, blue, and three-phase customer. A very useful customized function in visualization is added. Once the user clicks the Add Adjacent Circuit button, all the neighboring circuits connectivities with customer phase information will be displayed. Here's the example for wrong connection. Here's the example for wrong customer connections near the normal open switch. The left-hand side picture shows the customer in black dots as unknown phase customer, which can be defined by the dissimilar voltage pattern between 1 and 2. This group of black dots is located at the same pole of the open switch, which is the potential wrong customer connection. Then we rerun the phase models for the neighboring circuits after the group of black dots being moved into neighboring circuit. The similarity can be realized by the comparison between 1 and 3. 3,800 cases wrong customer connection has been identified and corrected near the switches. Here's the example of wrong customer connection in the middle of the circuit. Generally, the error happens between the big block commercial buildings with underground cable, which hard to find well street view map, even site visit. We are using pattern recognition to check the customer with unknown phase with all neighboring circuits to confirm which circuits does the customer belong to. 500 cases has been identified as in the middle of the circuit. Please note that In the backend system, the list of wrong connections has already been detected and sent through automatic email. The manual check helps to verify the result of wrong customer connection. So the second one is phase measurement. Phase measurement is the second one is impedance measurement. The impedance measurement is to monitor and detect degradation and broken service neutral. Here's a tragic story happened in Perth, Western Australia. Young girls got a massive electric shock by touching water tap in the front yard. Cause of the shock was neutral conductor melted after prolonged heating. This tragedy shouldn't happen if proactive detection or monitoring of the service neutral is in place. An important lesson for utilities company, we should always have detected, repaired the problems before customer report any electric shock to us. Well, it matches our slogan, safety always comes first. By applying our impedance measurement, the following lists can be achieved. Firstly, minimize the number of customers from getting electric shock. Secondly, day-to-day monitoring and proactive maintenance to replace existing service testing procedures. That is estimates a huge saving. By measuring the change in voltage due to the change in customer load current, the impedance from the supply source to the customer connection point can be determined. Impedance value is equal to the voltage difference between two consecutive time points as delta V over two current difference between two consecutive time points as delta I. Here's a typical neutral fault pattern where a slightly current rise causes a significant voltage drop. You may think delta V over delta I is too simple. Here's an example of our impedance algorithms which can overcome the issue of abnormal pattern. Delta V, delta I calculation result of 2.2 ohms in the case doesn't reflect neutral issues from this customer. Our algorithm has smart filtering function to avoid the impedance result being affected by voltage and current fluctuation. Here's an example of impedance for customer who has PV system. The impedance fault means a slightly current rise causes a significant voltage drop. In another way, a slightly current drop by reverse current causes a significant voltage rise. The voltage rise over the voltage co-limit causes the PV inverter trip off, where you can see the fluctuation between voltage and current. After impedance fault has been repaired, the voltage level is back to normal, and there's around 40% more capacity for PV generation. As safety requirements from government, the utility need to check integration of supply service line neutral, well, 1 in 10 years testing, but we couldn't fully rely on point-in-time maintenance activities before we run out of luck. Based on 5 minutes snapshot voltage cover power factor data, neutral impedance monitoring is taking place of the program and checking impedance result on a daily basis. The functionalities has been successfully tested and rolled out in later 2018. When Jemena fuels resource is dispatched to the location with suspect broken supply neutrals, the accuracy of pinpointing high impedance connection is nearly 100%. So far, 450 cases with neutral issue has been identified and addressed. The warning threshold now is down to impedance calculation of 1.2 ohm, which could prevent customer from getting a low to medium range risk of an electric shock, as well as avoid a potential fault by heating cable. For customer safety, our fuel crew will disconnect supply until neutral issue has been fixed. In the future, proactive maintenance function based on regression algorithm will be implemented to track the ratio of degradation and forecast the time to fail. The function will help us observe the neutral condition in advance before they reach the threshold. In this slide, 6 select photos with impedance issue are listed. The faults are not that obvious, where the customer can easily find by themselves. For example, the fuse overhead line connection box, customer never ever open it. So, to sum up, our sensitive model provides high accuracy to minimize the safety risk as well as reduce the chance for the field crew visiting the site without a neutral issue. After we have gone through the individual faults, let's move on the network fault analysis. The purpose of doing network analysis model is to get a provision of LV network backbone profiles, which can be considered as maximizing the smart meter benefits without installing any additional data collectors. To improve LV model accuracy and also to support quality of supply investigation and proactive improvement. Network fault analysis model is that once customer supply phase is known, perform nodal analysis using network connectivity model, line impedance, smart meter voltage and current to derive backbone profile on the LV distribution circuit. Then a pattern recognition function is used to analyze and detect the abnormal voltage and current patterns in the circuit. The fault type and its location can be identified. Here's the estimation of substation profiles, voltage and current in a three-phase showing in these two pictures. Let's look at the neutral bridge connection fault. I'd like to introduce the way we detect and rectify the fault. Step 1 is to identify the abnormal pattern. In the graph, you can see three-phase voltage is unbalanced. The unbalance is not caused by the load, and most likely there's a problem with the return path. Step 2, in our ad hoc analysis mode, once our users select substation and the data information, the pop-up icon with estimate fault information will appear at the estimate fault location in visualization tool. Our field crew were dispatched to location where the network fault analysis model identified. They found a clamp failure near the substation. The fault is not obvious to see due to the size of assets and the observation angle. Without fault location results, our field crews definitely need to spend more time to checking along the feeder, finding the fault. After the field crew fixed the neutral bridge connection issue, the operator needs to make sure all the fault has been addressed. Based on three-phase voltage pattern before and after the repair, this fault case can be closed. After reviewing the performance of LV network and rectifying relative faults, we need to find the best way to improve DR hosting capacity. In Australia, customers like to install rooftop solar panels that are connected into LV network. According to our record, 80% of supply quality complaints relative to solar PV customer inverter tripping due to overvoltage. Voltage compliance assists with DR planning and play particularly important role of the government's solar homes program. The idea of improving DR hosting capacity contains optimized Zhong substation, where Zhong substation is higher voltage substation supplies hundreds of distribution substations, optimized distribution substation, and optimized customer supply point. Ideally, by tapping up or down the voltage level at Zhong substation and the distribution substation in an optimal way, most of over or under voltage issue will be resolved. Then the rest of voltage issue can be resolved by optimized customer supply point. So the key question is to achieve DR integration will be how to deal with the voltage issue between Zhong substation and the distribution substation, how to deal with voltage issue between distribution substation and customer supply point. So before the platform was established, there were only few power quality meters installed at the end of the feeder, which couldn't support the full vision between HV and LV. Smart meter data and visualization tool provide an overview of Zhong substation with all belonging distribution substations. Well, the white door here is the Zhong substation. The door with other color is the distribution substation on the different HV feeders. By analyzing optimization of Zhong substation and distribution substation in a pair, it creates insights for suggestion for the business to make economic decision. For example, when the heat map overlays in a big proportion, which means the density of overload under voltage event is high, our model can provide recommendations for the end user to consider adjusting the Zhong substation tap setting. On the other hand, when the heat map is dispersed, the end user should check tap setting for distribution substation. And you can see here, the voltage problematic location with high density of events. Based on this location, how to choose which substation tap setting need to be changed in our HV feeder will be the next question. So let's zoom in into the potential voltage problematic location. So the mean custom voltage and the voltage scale by the type ratio are provided in arrow bar chart. In the chart, the feeder information starting from left-hand side, and the ideal voltage curve along the HV feeder should be like a horizontal line. When the mean custom voltage of the substation are lower than the downstream voltage, we need to tap up the distribution substation settings. For example, these three distribution substation, we need to increase the voltage for these three distribution substation. So the tool helps to identify the wrong tap settings substations and rectify the voltage issues before customers identifies. Traditionally, there's this type of non-compliance was not identified until customer report. Here's a good example for fixing compliance voltage issue by change transformer type ratio. The storage starting from a customer complained about his PV inverter trip off due to high network voltage. Our power quality engineer investigates the voltage level of distribution substation while analytic platform. They found the red phase voltage was higher than voltage limit during the PV generation period. At the same time, the voltage in the other two phases were close to the upper voltage limit. So this evidence can be used to make decision of tripping transformer tap ratio down. After transformer ratio was changed, the hosting capacity of the individual PV customer in substation has been improved. And you can see compared to before and after, as well as the total distribution substation. That's around 30% more capacity. We also developing a model. Here's another good example of fixing compliance voltage issue by changing customer phase connection. Apart from all the PV customers affected by substation voltage, we see the individual customer voltage is higher during summer day, and it rises to great voltage level outside the code limit, where PV inverter trip off. It also causes downstream customer in the same phase to experience the high voltage. Technically speaking, swapping customer phase connection to a lower voltage phase is a good, cost-efficient way to solve such voltage problem. You can see here the phase is changed from one phase to the other, and the voltage problem has been solved. Traditionally, those DR integration issues were resolved by LV homologation work, which costs thousands of dollars of the business, includes several days site visits. So now the desktop analysis can cut the cost. We are also developing a model to see the impact of new PV service on distribution network. In this example, after we import the distribution curve as a customer with new PV connection into the model, the impact of the voltage difference can be realized. And you can see the two curves. That's the voltage difference. These tools can also be used to evaluate the impact of other DR service, such as battery system, electric vehicle, once we know the pattern of charging or discharging. In the future, proactive DR planning will be implemented based on this simulation tool. So let's move to the conclusion session. So far, we have successfully supported our analytic work. However, our journey is not end yet. In Jemena, other major projects by using smart meter data are power changes for residential demand response, Jemena solar-friendly neighborhood project for active load control, demand reduction trial for voltage regulation, and the EV charging trial for testing the technology. That's all about my presentation today. Thank you for the support from. Thank you for all the audience. Do you have any questions?
Thank you. That was a really fantastic and comprehensive presentation with a lot of information. And so, yeah, thank you for giving such a great presentation.